Um, okay, so I'd like to welcome minjoonseo from University of Washington, who's a PhD student, and he's going to talk to us in this series of cognitive speaker series. He's going to give us a talk on neural speed reading. Over to you, Minjoon.
Okay, yeah, thanks for the introduction. Hi, so I'll be talking about neural speed reading. This is joint work with Saewon Min, Ali Farhadi, and Hana Hajishirzi from SNU in Korea and also from UW. So I'll get started. So let's first take a look at sentiment classification task, and which many people use recurrent neural network to classify a sentence such as like intelligent and invigorating film into a class of positive or negative sentiment. And I think it's very obvious how people use RNN to do the sentiment classification. They usually use each word as an input to the RNN, and they start with some zero hidden state or some initial hidden state, and basically recurrently update the hidden state as they see the input word, and at the end they might use the last hidden state, or they might use sum or take a max over all the hidden states to classify into sentiment. I think this is very typical way to use RNN on sentiment classification. So now what I want to point out first is that RNNs are quite slow. And one of the reasons that RNNs are slow is because they cannot be parallelized over time. So the time complexity is strictly linear in the length of sequence. And of course, GPUs cannot take full advantage of parallelization in this case, and which makes basically very hard to overcome RNNs, and hence a lot of research focus also on overcoming the slowness of RNNs, such as recent Google's Transformer or Facebook's CNN-based MT. So this work will be also focusing on how we can overcome the slow RNNs. But then now I want to also point out that CPUs are not that great for RNNs either. So of course GPUs might not be that great because you cannot take full advantage of parallelization, but also CPUs are not that much great because neural networks require so many computations, and usually that means CPUs are quite slow anyways. So let's take a look at why it's so costly for CPUs to compute RNN. So here's a very rough complexity, flop complexity, flopping the float operation, number of float operations of RNN. So if you consider hidden state to be size of D, and let's just assume that the input is also size D for just ease of explanation, but it could be anything. Then we see that we need a 3D plus 2D square operations to compute simple RNN. And it's quite apparent that here, if D is sufficiently large, then matrix multiplication is the bottleneck. And matrix multiplication is basically what causes D square, or the D square, the quadratic time complexity. So basically what we want to do is how we can overcome that. And can we improve then inference speed on CPUs? Can we actually reduce this flop number of operations for the RNN? And of course, you might wonder why not use GPUs. And my answer one is that CPUs are often more desirable option for production, mainly because there are more CPUs, and then GPUs require a lot of, it's more expensive usually. But then also for small devices, CPUs are usually better because they only have CPUs. And also, if you're talking about latency critical applications, then CPUs can have lower latency. So CPUs are pretty important things to consider. So now, how can we actually speed things up on CPUs? And we basically want to think how humans actually make reading fast, or how they make they actually understand text fast. And it has been pointed out that the speed readers, people who read fast, skim unimportant parts and fully read important text. So our question is, can we actually make the RNN do a similar thing? And if you think about reading, then RNN's reading is quite, RNN's recurrent update is quite similar to reading. So recurrent update being the matrix multiplication here. So then we can define scheming as using smaller matrix multiplication and fully reading as using big matrix multiplication. Then basically, if we can switch between these two, if the model can switch between scheming and fully reading as it needs to be, then we can basically have a similar scheming ability to human readers. So let's take a look visually how this could work. For instance, let's take a look at this same example, the intelligent and invigorating film. So given okay, I was muted, so yeah, I'm muted again. Yep. So given this word, so given the word intelligent, we basically want to first determine whether this word is important, and then basically determining that this word is important will let us the RNN will decide to read it. In this case, we update entire hidden state, just regular RNN. But then the interesting thing happens when the input word is not important. For instance, let's take a look at and because this word is not important, we'll decide to skim. And when we decide to skim, the decision function here, the square, will output 2, q2 equal to 2, and in this case, we use a small RNN to just get a new hidden state that's smaller than the entire hidden state, and basically we only update the first few dimensions, and the other dimensions will be copied from the previous hidden state. So in this case, then we are just updating the first few dimensions. And we basically do similar things. It's quite simple as this. So then in addition to the recurrent neural net, the big RNN, we basically have two more components. One is the small RNN, and the other is this decision function, the square that outputs the Q value to decide whether the current input is important or not, and then deciding whether to update the entire hidden state or just the first few dimensions. So that's actually it for the model. And in summary, the schema RNN consists of two RNNs. One is big RNN with hidden state size D, and the other is small RNN with hidden state size D prime. And usually D will be much bigger than D prime. So for instance, we can have D equal 100 and D prime being 5. And hidden state is shared between the two RNNs. And of course, big RNN updates the entire hidden state, but small RNN only updates the first few dimensions of hidden state. That's the main point of schema RNN, to summarize it. So when we're using small RNN, then the inference requires smaller number of full operations, because the small hidden state basically makes the update only D prime times D, which is much smaller than D square. And if we can make dynamic decision on which size of RNN to use, then basically we can obtain speed advantage over using just big RNN all the time. So I hope that's good. That's very clear. So now the issue is, though, the model is quite simple. The inference model is quite simple, but an issue could be how we can train this, because the decision functions are non-differentiable. So how people usually try to overcome this issue is that one way they use something like policy gradient, pretty very classic algorithm that can estimate the gradient. And the good part of this estimation is that gradient is unbiased. But then it has been noted very many times that the estimation has very high variance, which means that it's very hard to train. And another option could be biased estimation, but which could have a low variance, such as Gumbel softmax that has been recently proposed. And the good thing about this is that it's very easy to train compared to policy gradient according to our experiments. And also it makes the model fully differentiable during training by the reparameterization. So I will not go into detail of this. You can just assume that the Gumbel softmax is a algorithm that can help us to estimate the gradient of a model that has non-differentiable components. So I'll hence skip this part. So a recent work that's relevant to ours is LSTM jump. And it is an orthogonal work in that it has been concurrent work, but also it is a bit different because the work tries to skip things. But then we think that skipping and skimming is different thing. Skipping is ignore the word or a segment of a sentence entirely. Skimming is that you still consider them, you still read them. It's just that you spend less time, or you use the smaller RNN and smaller matrix to update hidden state. And of course, we can consider combining them, but although it has not been considered in this work. So just to point out related work in case you're interested. And let's now take a look at the and then of course, schema-RNN has output for every time step also. This is another advantage of schema-RNN because LSTM jump, if you're skipping words, then you will not have some outputs for those skipped words. Although LSTM jump has some GPU advantage. So let's now go into the experiments.
Can you take a quick interrupt, Minjoon? Somebody's asking in the chat where they can download the schema-RNN model and data sets.
Okay, so we're planning to release it soon. It's not ready yet. Yep. So hopefully in the next version of our paper, we can point out where the model is. I mean, the code is.
So what, it is like in a month, something like that? In a month's time?
Probably. Yeah, I think so. Yeah, we hope so.
Okay.
Yeah.
Okay.
Yep.
Thank you.
Thank you. Yeah. So because the paper's deadline is about in a month, so hopefully. So the first is the classification result. So I show you the sentiment classification results, which was extracted from the IMDb. Basically, all these task SSST, Rotten Tomatoes, IMDb, and Asian News, they are all classification tasks. And then we see an interesting thing. One is that, so we have to look into this. First of all, our model compared to standard, which is just using LSTM without any skimming, our model is getting a similar or better accuracy in general than standard models, I mean LSTM. And that basically points out that our model is not losing accuracy even though we're skimming. And second thing we want to look into is this, the fourth column for each task, which is the speed up, and also a third column, which is flop R. So that means that we're gaining speed up of 2.4 and 1.4 for the first SST task for the first row of the skimming. And we see a similar trend in other tasks too. Like for instance, in Rotten Tomatoes, we're getting 2.1 times reduction in flop and 1.3 times reduction, the boost in the speed. So basically, the point is that although, of course, the speed and flop reduction is not that large, but we're seeing non-trivial speed up and flop reduction, even though we are using, while we're maintaining similar or better accuracy than the LSTM. And that's basically proving that the skimming mechanism is not losing accuracy, kind of similar to how humans would do. Of course, humans could still lose accuracy by doing skimming, but then if you are skimming unimportant parts, then most likely it will not affect the goal that you have when you're reading the text. Of course, in this case, the goal that the model has is to classify the sentence into the target sentiment or any downstream task. I also want to point out that our model is better than LSTM jump in terms of accuracy and also the speed up. So that's showing that it actually works on real data set. And also we have done this on question answering, which is the squad in this case. And I used my previous model, which is BiDef, that basically obtains about 77.3% accuracy. You can see that at the bottom. And basically the point here again is that we also use the skimming LSTM or the skimming LSTM, replacing the existing LSTM in the BiDef with the skimming LSTM, and we are only dropping by 0.2% F1, the bottom row, SK BiDef, but then we gain the speed up of 1.7 in the flop reduction. So actually, one thing I wanted to actually point out is that I forgot to mention this: the flop reduction and speed up is actually different measures, because flop reduction is how much we would reduce the number of operations, but then the actual speed up, benchmark speed up might be different. And we had a benchmark for the classification task in this case. That's why we have the SP column. But then the main purpose of this work was not to actually benchmark the speed up, but then more of a benchmark with whether we can reduce the flop reduction. So that's in this task, we didn't have that yet. And we hope to have that in future, although I don't know when that will be. So, but then the main point I wanted to point out is that basically existing LSTM can be replaced with this kind of skimming mechanism that can obtain the flop reduction rates without losing accuracy quite stably. That's the main point of these experiments. And now I'll move on to the more of a F1 and flop. Actually, I'll skip this due to time constraint. But then now let's go into the visualization part. So
there is a question for you in the chat. If you want to take it, it's up to you. How are you quantitatively measuring communicated understanding of recipient to compare skimming?
Oh, okay. Sorry. I was not actually looking into the chat. I'm sorry. I thought that was after the talk. Sorry about that. Yeah. So sorry about that. So which one is it?
No, sorry. Just if you want to take it, it's up to you if it's a good time.
Oh, okay. All right. So that's the.
How are you quantitatively measuring communicated understanding of recipient to compare skimming?
Oh, okay. In this case, basically, that's measured by the the accuracy of the model of for instance, if I'm doing sentiment classification, how accurate whether model can classify into. So that's all we did. Although I also agree that maybe there could be more interesting thing that we can try to quantify the understanding. So in this case, the classification result accuracy is the quantification. But then also I think this analysis can be not quantitative, but somewhat qualitative proof that actually the model is actually doing something interesting. For instance, in this case, the model, we basically visualize which words the model decided to skim and which words it decided to fully read instead of skimming. So the blue words are the words that got fully read, and black words are skimmed. And as we see, if you just look at the blue words for the positive sentiments, liked because good, dramatized, greatly enjoyed, overall good movie, good. So it's basically just focusing on really important parts of the sentence that actually shows what the sentiment should be. So it's kind of goal driven, of course. When the model is reading the sentence and it has a different goal, then it will need to focus on different parts of the text. But if its goal is to classify the sentiment, then basically it reads these kind of words that's very important for classifying the sentiment. And similarly, when we are looking into negative sentence, then we also see that the words that it focuses on or fully read is very important sentiment words such as no, 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 entire, revolting, dreadful, new, ridiculous, tiresome, got worse words. So basically the model is actually quite successfully determining whether it should read carefully or it should skim if it's not important. So I'll just take a look at it. Okay, yeah, so, and then we're kind of saying similar thing in the question answering too. Because if you see here, the question is, what is one straightforward case of probabilistic test? Then basically the model is goal driven, so it has this question in mind that it needs to answer this question. And if you look into the words that the model focuses on, such as simple probabilistic test, format probability test, it's very relevant to the question, right? And you basically look into only these words as you read the entire context, and you skip the words that are not relevant to the question, or if the model thinks that that's not important to answer the question. So that's visualization of the QA system. And now let's go into more visualizations. And another interesting part of the scheming is that, of course, many modern models have several layers. Like in this case, we have 2 layers. One is the first 2 layers are forward and backward layers of LSTM, and the second two layers are the forward backward of the second layer, of course. And we see that actually one interesting phenomenon here is that the model skims a lot in the second layer. It doesn't skim that much in the first layer, which means that in the first two layers, the model is very they're trying to look into very details, or they're looking into very low level things. But then when they go to the second layer, the second FW and second backward, they skim a lot, and that means that now it's trying to just look at the important ones, and that's very aligning with the intuition that the model tries to skim when it's not important. And of course, in high level layer, then a lot of things will be not important than the lower layers. And also another interesting thing we can do with this kind of model is that because the skimming, whether the decision to make a skimming is basically thresholded. So for instance, if the decision function outputs 0.7, then it will skim, and if it outputs 0.3, then it decides not to skim. Then in this case, we can threshold by 0.5. We can control this threshold. We can maybe skim only when the threshold is very high, like 0.8. Then we can basically make the model to skim more at the runtime. And as we see, the blue one is the skim RNN, and the red one is basically the skipping, where the small hidden state size is basically 0. That we see more better curve of F1 versus flop reduction than the skipping. So this is actually showing that the skimming is better than, or working better than, the skipping. And also, of course, we can dynamically control the number of flop at the runtime. So this is now almost the end of talk. Last thing is, of course, what I told you before is whether the flop reduction or the number of flop operation is equivalent to speed. This is not true in GPU because GPU can parallelize. So basically, number of flop operations is not as important as how much you can parallelize in GPU. On CPU, it's conditionally yes, but then it will require low-level programming. So one thing I wanted to just let you know regarding the code, if we actually release it in 1 month, is that we basically, in order to actually take full advantage of this kind of speed up, we need to do low-level programming because there's so much overhead in the typical TensorFlow, PyTorch, this kind of packages. But we still see a definite flop reduction. That's I can tell with this code that we'll release. So I'll actually skip this, and I think I'll now conclude my talk. So I introduced a schema RNN, basically that's switching between two different size RNNs with shared hidden states. And of course, this can be generalized to multiple RNNs that share the single hidden state. And what I wanted to show here is that basically we can have a different agents. I mean, each RNN can be constrained agent, and each agent has a different speed. But they can basically share the same hidden states and then operate on the same input sequence. And we can basically make a decision function that decide which RNN to use at each time step. And that can be pretty efficient and also works well. And then not without losing accuracy or the downstream task accuracy. And speed gain can be substantial. In our case, we saw up to something like 3 to 4 times speed up. And of course, this can be more beneficial with the larger hidden state size because there are a lot of overheads with small hidden states. And I think this will be especially useful for latency because GPUs sometimes cannot get much better latency than CPU, even though it has very high throughput. But of course, again, if we really need to take advantage of this, then we will need to go low level. So future work we will be using multiple RNNs and also extension to latency critical applications like speech and video, and low level implementation will be critical to actually observe the benchmarked speed up. Yeah, so thanks a lot. That will be all for my talk.
Thank you so much, Minjoon, for the great talk. Are there any questions from anybody? And if there aren't, or while people are thinking, I think, did you skip slide 34, the TensorFlow or PyTorch slides?
Oh yeah, I did.
Do you want to tell us while people are getting their questions ready?
Oh yeah, sure.
Yeah. Yes.
So yeah, one thing interesting was that So TensorFlow and PyTorch had a lot of overheads. That's what I saw. So for instance, if I actually measured how fast it is at inference time, actually for small enough hidden state size, NumPy was faster. So actually I benchmark on NumPy. I just wanted to tell you because the graph that I show here is benchmark based on NumPy, not TensorFlow PyTorch. And just to give you a number, when I experiment on this, basically hidden state size smaller than 220, the TensorFlow was slower than NumPy, and hidden state size smaller than 700, PyTorch was slower than NumPy. So when the hidden state size became big enough, NumPy became slower than TensorFlow, which I think is mainly because TensorFlow can take advantage of more advanced, I guess, low-level libraries. That's, I think, all, yeah, for this slide.
Oh, great, great. There is another question in the chat from Tongo. Is it possible to get better speed up with quantization?
So I think definitely that's some orthogonal direction, although I'm not too familiar with quantization though. So I think that could be a yeah, so yeah, I'm not too sure about it though. Yeah, sorry, but I think definitely that's something that we can try out. Yeah.
And I see another question from Jim Sporer. How do we get from pattern recognition to reasoning? Is that a future direction?
Yeah, so I think that's very of course very in long term, yeah, I think that's a good future direction. Although in this case, I think we cannot really say this is reasoning. It's more of a, as you say, it's pattern recognition. And personally, yeah, I'm really interested in reasoning. Yeah.
Oh, and then there's a question from Salim. Was puzzled by squad. So it is 10 points higher than the table you showed. So yeah, if you go back to that slide.
Oh yeah. So one thing is that this is when we submit the paper, and we only use the published paper. I think there are more unpublished papers. We just actually did not show that. Yeah, at the time of writing this, among the published paper, it was state of the art. But then I think a lot of papers came out into the concurrent iClear submission, and this should be updated to like something like 88. I mean, single model something like 86%, I think. So I think you're correct. Yeah. So it got improved a lot in recent like few months.
Salim, are you okay with that answer? Is that okay? Looking to see if there's any other questions. I don't see any more. So, so which conference is your paper going to be at?
In the iClear 2018.
Okay. Oh yes, you said yeah. Okay.
So actually, this is actually exactly from the paper. That's why the state of the art is not up to date, because it was from the November. So I will have to update this paper soon. Yeah.
Okay. Well, you have a very attentive audience. You can see. Okay. Yeah, any more? Anybody want to say anything verbally? Gosh, I can't believe you got it done in time, Minjoon. When I saw your slides, I thought it was impossible.
Yeah, I skipped a lot, and also there were a lot of animation. That's why. So yeah.
Yes. Yeah. So for everybody, Minjoon is actually physically in Korea at the moment. So maybe he's been watching some Olympics. Oh, yeah, you're getting more. Thank you. Thank you.
Thank you so much.
Thank you.
Great to talk here. Thanks a lot. So I think that's it then.
So yes, it is. Thank you so much, Minjoon, and I hope you'll join some of our other calls.
Okay. Yeah. Thanks a lot.
And good luck with the paper and everything.
Okay. Yeah. Okay. Happy New Year too. Yeah. Thanks.
Happy New Year.
Yeah.